Mm, yeah. Good. 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 Oh, good. Good. All right. So, what was this question from the exam?
So it was the center of mass problem.
Okay.
The function was 1 minus x to the fourth.
So our function was 1 minus x to the fourth.
Then two x coordinates, -1 and 1.
Right.
So I know that.
And so you want to find the center of mass of the area bounded by this and the x-axis, I'm assuming? Okay.
I found x bar to be 0 because of symmetry.
Sure.
The area to be like 8/5, but somewhere along the lines, I was
All right.
side bar.
All right, let's figure it out. And let me go ahead and so B. And today is the 29th. This function's a little bit exaggerated. It's kind of like that. And yes, our center of mass should be somewhere here. I'm betting it's below the midway point because more of the area is on the bottom of this shape than the top of this shape. But not much, because this shape is kind of, it looks, if you graph this, it looks pretty square actually, or pretty rectangular. And actually, if it was one, you can even go further, like it was 1 minus x to the sixth, it's even more like a rectangle. The higher the even power is, the more rectangular it looks. So let's go ahead and find our center of mass, our x bar, y bar, and we're pretty confident that x bar is equal to 0. Y bar we have to work for. So to find y bar is going to be your moment around the x-axis divided by your mass, or as we typically write it, it's the integral of whatever divided by your area. And that integral is the one that's kind of tough. But let's talk about the area first. So the area should be just the integral from -1 to 1 of 1 minus x to the fourth dx. If you wanted to, you could do the thing where you say it's the integral from 0 to 1 of 1 minus x to the fourth, and then double it. Either way is fine. Either way, we should get the same thing. Here we get x minus x to the fifth over 5 from -1 to 1, which is 1 minus 1/5 minus -1 plus 1/5, which is going to be 4/5 plus 4/5, which is 8/5. Or here it's 2 times 4/5, which is 8/5. So now we just have to find the moment around the x-axis, which is always the pain in the butt. Yeah, it's especially a pain here. So, oh, no, yeah, yeah, it is. There's actually a couple ways you could do this. Sorry, let me fix this here real quick. 1 second. That's not what I meant to do. Wow, can I do that? Okay, there we go. Finally. All right. So, at the moment around the x-axis, doing this what I would consider the more typical way, leaving things in terms of x. We're thinking about a vertical rectangle here, all of its mass being put at the center of that rectangle, and that length of that center being the distance of the lever arm, and then all the mass being the area of that rectangle. So that should end up being the integral of the height of that thing, which is 1/2 of however tall my function is. And then the area of that rectangle is my function times dx. Or in other words, 1/2 your top function squared minus your bottom function squared. Because my top function is f of x equals 1 minus x to the fourth, and my bottom function is unexcitingly y equals 0. questions about this before we keep going? I mean, do one thing in the chat here. I will point out there's another way to do this problem though, which I want to show you because I think it's worthwhile. Sorry, something's loading here. 1 second, please. There we go. So those of you just joining us, we're talking about one of the exam problems from Babson's test yesterday. So this is going to end up being 1/2 the integral from -1 to 1. I'm going to multiply this out and get 1 minus 2x to the 4th plus x to the 8th. I'm going to do the usual trick of that's an even function. So I'm going to rewrite this as 1/2 times 2 times the integral from 0 to 1 of 1 minus 2x to the 4th plus x to the 8th. That's going to be 1 times the integral of this is x minus 2x to the 5th over 5 plus x to the 9th over 9 evaluated from 0 to 1, which is just going to end up being 1 minus 2/5 plus 1/9. And if you're real short on time, you could just throw that in your numerator and be done with it. We can simplify it though. 45ths, I guess, is my common denominator here. So it's 45 over 45 minus 18 over 45 plus 5 over 45, which ends up being 50 minus 18 is 32 over 45. And now, no, I'm not worried yet. Okay, cool. I was almost worried. So then my y bar coordinate should be 32 over 45 divided by 8 over 5, which is 32 over 45 times 5 over 8. It's a 5 there, sorry. That's going to be 32 over 8 times 5 over 45, which is 4 times 1/9, which is 4 over 9. As predicted, slightly lower than the 1/2 high mark, which is great, right? We expected it to be just a little bit lower than 1/2 because more of the area is on the bottom than on the top. Seems reasonable. Alternatively, if you had wanted to, you could have done this one totally differently. Here's what I mean. So usually we think of things in terms of x as far as center of mass goes, as far as finding a moment, but we could have also done this one in terms of y. So I'm going to draw my function again. And I know that doesn't look perfect, but fine. I'll point out that the right half, instead of writing it as f of x equal to 1 minus x to the 4th, I'm going to solve for y and say y equals 1 minus x to the 4th, x to the 4th equals 1 minus y, and x equals plus or minus the 4th root of 1 minus y. The right side is x equal to the positive 4th root of 1 minus y. The left side is x equal to the negative 4th root of 1 minus y. So then you can do this one. What I would, I might be shooting myself in the foot here. I'm going to set it up. It might not work out to integrate, but we'll still, oh, it probably will. It's just probably going to be not any better. So now we're thinking about this area, all this lever arm distance away, where the lever arm distance is y, and the area of that is the length of my strip times dy, which is the right side minus the left side. So my area of my strip is the 4th root of 1 minus y minus the negative of the 4th root of 1 minus y, which is just 2 times y, 1 minus y to the 1/4 power. And my lever arm is y, so my moment around the x-axis is going to be the integral from y equals 0 to y equals 1 of my lever arm y times my area of my strip, which is 2 times 1 minus y to the 1/4 dy. Which, okay, doesn't look great, but it's not as bad as it looks. It's still pretty bad though. But so to fix this, or I should say, to be able to integrate this, we would do a u substitution with a back substitution. So I probably haven't made this problem any easier to do. I thought it was going to be easier because it's like using the less terrible version of the moment formula, where it's just your variable multiplied by your function. But this would look like if I let u equal y, sorry, u equal 1 minus y. And then my du is negative dy, so negative du is dy. This is going to end up looking like the integral, my y becomes 1 minus u The 2 gets to live out in front, and my 1 minus y becomes u to the 1/4. And then we have a negative du over here. My new, oh my gosh, the words coming out of my mouth. My new limits of integration are, instead of 0, 1 minus 0, instead of 1, 1 minus 1. So then we could fix this. We could get rid of this negative sign by interchanging those and get 2 integral from 0 to 1. Multiply this out. You get u to the 1/4 minus u to the 5/4 du. I lost the negative sign by interchanging the order of the limits of integration. And then finally, we integrate, we get u to the 5/4 divided by 5/4 minus u to the 9/4. Yeah, 9/4 divided by 9/4 from 0 to 1. And we pray it's the same answer. You get 2 times 4/5 minus 4/9, which is going to be 2 times 36 minus 20 45ths, which ends up being 16 times 2 is 32 45ths. Is that the same? Yes, it's the same. Good. So what was the point of doing that? I don't know. I thought I had a good answer, but the point was to see that you could do it the other way. Now I will say, when you get to 21D, hopefully you will talk about moments again, because you will see that both of these formulas are actually the same formula. They're just coming from the fact that you're doing a double integral one way versus the other way, where you're doing first x then y or first y then x. But it's always, whenever you're finding a moment around an axis, it's always just the double integral of the lever arm. End of story. And then the rest of it comes from doing the double integral, which I know doesn't make a whole lot of sense right now, but it will eventually. So when you get around to 21D, if you talk about moments, try to remember this, because it's kind of neat. It's kind of nice to see how much easier it is to do with double integrals than with single integrals. All right. So that problem looks like it was not too awful, but still the numbers are not great. It was a little bit messy. I guess before we start talking about polar coordinates, are there any other questions about the exam that many of you took yesterday? I know it's hard to remember what was on the exam exactly, so if there aren't, that's totally fine. But if you want to torture yourself by asking questions about the exam that hasn't been graded yet, you're more than welcome to. Great. Polar coordinates. Yes, I can. Let me actually do myself a favor and move this up a little bit. Okay. So polar coordinates are another way of describing a point in two-dimensional space. So Cartesian coordinates, which you're very used to, just your usual x and y. Just to be very specific, to locate that point, we move x horizontally and y vertically. Not that you don't all know that, but just to remind ourselves how that works. So for example, if I want to find the point, x comma y, I move over a value of x and up a value of y, assuming x and y are both positive. And there's my point, x comma y. Polar coordinates are very different. Polar coordinates, we can get to any point in the xy plane by, you can kind of think of it either way, by first rotating an angle of theta, whatever that angle needs to be, and then moving in that direction. Enough, a length of r. So if I wanted to get to the same point over there, instead of going over and up, what I'm thinking about doing is I'm thinking about rotating an angle theta from the positive x-axis and then moving from the origin in that direction of the angle theta, a length of r. And usually we label this as r comma theta, meaning we label the length first and the angle second. That is typical labeling notation for polar coordinates. Um, yeah. Unfortunately, sometimes someone might write a coordinate and you're not sure what they mean, right? Like if I wrote, for example, well, super annoyingly, if I wrote the coordinate 1 comma 0, it's actually the same either way in polar or rectangular coordinates. You go over 1 and up 0, or you go a distance of 1 where the angle is 0. Oh, that's the same spot in the other way. But people should be explicit about what type of coordinate system they're using. It's usually obvious unless your angle is not some obvious angle. Like 0 is not always obvious that it's an angle versus just a coordinate. Um, if we kind of put these two pictures on top of each other, we can find the relationship between our polar and our rectangular coordinates. So none of this should be surprising so far. We're going to get the typical equations: x squared plus y squared equal to r squared, just coming from the Pythagorean theorem. Taking cosine of theta, we can see that cosine of theta is equal to x over r, so that, bless you, x is equal to r times cosine of theta. And similarly, sine of theta is y over r, so y is equal to r times sine of theta. And this last one, I feel like we don't use all that much, but it's also true. The tangent of theta is equal to y over x, or somewhat equivalently, the arctangent or inverse tangent of y over x is equal to theta. Although you have to be careful here because arctangent only spits out angles between negative pi over 2 and pi over 2, or negative 90 degrees and positive 90 degrees, where your angle could be an angle that was in quadrant 2 or 3. So we'll talk about that a little bit more as we go along here. A couple other things to be aware of here. With polar coordinates, a negative r value means we face the direction of theta and then move backwards, or move in the opposite direction. So for example, if this point up here is r comma theta, then moving in the opposite direction, the same length, this would be negative r comma theta. Or, and this is what's kind of annoying here, equivalently, r comma theta plus pi radians. So here's what's kind of a bummer about polar coordinates. They're not unique. There are multiple ways of describing the same point using polar coordinates. Just like there's multiple ways of describing the same point on the unit circle using an angle and a distance. But it's not that big a deal. I mean, it's kind of a bummer just because we like things to be unique if possible, but fine. Also, you should feel free to ask questions along the way if you have them. So let's do a few things that aren't too terrible, and then we'll talk about some other stuff here. So let's find 3 different polar coordinates for each of the following Cartesian coordinates. So we'll do the first one together, then I'll let you all do the next one. So let's say our first one is x comma y equal to 2 comma 2. I'm going to graph it. So over 2, up 2. So there's our point using Cartesian coordinates. So now I'm trying to think about a way of writing an angle and a length. Well, the easiest answer to this, or one of the answers being the easiest one, is just to use the relationships. We know that r squared should equal x squared plus y squared. So in this situation, r squared is 2 squared plus 2 squared, which is 8. So r is equal to the square root of 8, or if you prefer to simplify that, it's equal to 2 root 2. And the angle, I don't think you need to use the arctangent function here to find that angle. If you go over a certain amount and up the same amount, I think we all know what the angle is. Write it down for yourself before I write it down. In radians, please. All these, definitely these coordinates do get written in radians. We typically do not use degrees unless, no, we just typically don't. So here, if we're going over 2 and up 2, that is definitely a 45, 45, 90 triangle, or my angle should be pi over 4 radians. So one way of writing this is r comma theta equal to 2 root 2 comma pi over 4. And now we just want to come up with two other answers. So another answer could be, say, 2 root 2 and just add a whole revolution to that angle. So you could add 2 pi to pi over 4. I'm even going to write it just as pi over 4 plus 2 pi, but then I should simplify that. That's 2 root 2, comma, pi plus 9 plus 8 pi over 4 is going to be 9 pi over 4. And then we could also say have gone halfway around and said my angle is pi over 4 plus pi, pointing in that direction. But then I'm going to make my r value negative 2 root 2. So that would be negative 2 root 2, comma 5 pi over 4. Literally, there's an infinite number of ways you could write this coordinate. You could keep adding 2 pi to this angle and get another way of writing it, which would be fruitless, but possible. Similarly, you could keep adding 2 pi to this one and get another way of writing that. Or you could subtract 2 pi as well. We also could have written this as negative 2 root 2, comma, negative 3 pi over 4, if we really felt like it. But usually we pick the lowest hanging fruit. You want to write it, we would always prefer to write it using a positive r value and an angle between 0 and 2 pi. So preference here, r is greater than or equal to 0, and your angle is between 0 and 2 pi. And yes, r can be 0. That's just the point. That's just the point that's the origin. If r is 0, it doesn't matter what your angle is, because whatever direction you're pointing, you're going a length of 0. We probably don't need to do another one. I think that was enough of that. Yeah, question. Oh, cool. Sure, let's take a break for polar coordinates. Now, the polar coordinates aren't interesting, but they're not that interesting. The graphs are kind of challenging, though, I should say. Dx over x squared? Right. So this is a test question. So let me ask you first of all, let me ask anyone, what's the first thing I should be looking at here or be aware of? I know it's a very general question, but before I start doing anything, I need to think about the fact that this integral is, well, yeah, but more specifically, I don't know it's divergent yet, but I know it's improper. I know it's improper because that function, 1 over x squared, is undefined when x is equal to 0. So my very first step is going to be to write this as the integral, instead of from 0 to 1, from a to 1 of 1 over x squared, and then write the limit as a approaches 0 from which side? the right-hand side because we are between 0 and 1, meaning we're bigger than 0, meaning we are right of 0. And then I would probably rewrite it as the limit as a approaches 0 from the right of the integral from a to 1 of x to the negative second, just to make it easier to anti-differentiate. I'm going to rewrite it as the limit every step of the way of x to the negative 1 divided by negative 1 from a to 1. Now, this is where it's easy to fool yourself into thinking this converges. If you write it like this, in fact, let me do one more thing. Let me write as the limit as a approaches 0 from the right of negative x to the negative 1, because dividing by negative 1 is the same as multiplying by negative 1. And now if we plug in our limits of integration, we get the limit as a goes to 0 from the right of negative 1 to the negative 1 minus a to the negative 1. And this is a little bit dangerous because if you plug in 0 now, you might convince yourself that 0 to the negative 1 is equal to 0, and it's not. 0 to the negative 1 is division by 0, which is undefined. So what I would prefer to do is write this as the limit as a goes to 0 of 1 to any power is 1, so that's just negative 1 minus 1 over a. But then as a approaches 0, this part here approaches infinity, and so we end up getting that this integral is diverging, and it's diverging to, that seems wrong. I forgot the minus sign. Sorry. This should have been minus 1. So I was about to say it's diverging to negative infinity. And I know that's wrong because 1 over x squared is always positive. So you shouldn't be able to have a negative amount of area. So it's always good to think about what kind of answer we should be getting, even if it's divergent. I missed a minus sign from this step to this step. I wrote negative 1 to the negative 1, but I forgot that it was minus negative a to the negative 1, which is really minus negative 1 over a. So I really should have written this as the limit as a approaches 0 from the right of negative 1 plus 1 over a, which then goes to b plus. So we would say that this integral diverges, and if you were asked in which way, we would say it diverges to infinity. Sure. Those are always interesting. What was that question?
Like 1/1 plus squared x.
Sure.
That goes to like 0 to infinity, or is it the 1?
Hmm. Oh, like that? Okay.
Cosine squared x somewhere in there.
It's probably not going to matter either way. So, yeah, all right. So here's what we have to say. We're trying to do something with it. We're trying to do something with either with this or with this, right? But we're told, I assume in the problem, to use our previous work to help us do it. And here's the thing. If the thing you already know is divergent, and the thing that's impossible to integrate is something you're comparing against something else, if you're comparing against something divergent, you can only show it's divergent. So there's no way we could even think about considering this as being convergent. So here's what we need. To show something is divergent by comparison, we need to show that the function that we're trying to integrate or show is convergent or divergent. Let's just call this g of x for the moment, whatever g of x happens to be. We need to show that g of x is bigger than 1 over x squared. Because if your function is supposed to be divergent, it has to be bigger than some other divergent function. Conversely, if you're trying, that was a very bright light in my eyes. So conversely, if you're trying to something is convergent, you need to be smaller than some other function whose integral is convergent. So let's convince ourselves. Well, here's what I know. I know that either way, 1 plus cosine of x or 1 plus cosine squared of x, both of those, So, yes, I feel like it might have been cosine squared because I feel like 1 plus cosine is going to be problematic because 1 plus cosine squared is for sure always bigger than or equal to 1 because cosine squared is always bigger than or equal to 0. This, on the other hand, doesn't work out because this is between 0 and 2. And that's going to be problematic. When I invert it, it's not going to necessarily make it smaller. So I'm pretty sure we're safe to say it's this one, probably not this one. Oh, I've got some chat here that I did not see. What's in the chat? Oh, some answers. Yep. Well, someone wrote it was only cosine. Someone else wrote, I believe it was 1 over cosine squared or cosine. Yeah. Well, interesting. Yeah, interesting. I'm going to go with this because I know this is going to work. So let's pretend it was like this and see what happens. So this is bigger than or equal to 1. And it's, yeah, yeah. And then we are safe to multiply everything by x squared because x squared is always non-negative. So it will retain the inequality direction. And then if we invert both sides, when you invert both sides, that changes the direction of the inequality. Good? Just in case you're not sure about that, 2 is less than 3. 1/2 is bigger than 1/3. So then 1 over 1 plus cosine squared x squared. Uh-oh, I have a problem here. I'm less convinced. Uh-oh. So it's probably not that function, right? Because I've got this bigger than or equal to 1, and now this is less than or equal to that, but we know this integral is divergent, so being less than that's not helpful. So, it is without the 1. Okay. All right. So let's try this again. Apologies. Let's see if we can get it right here. So we're actually looking at this according to someone on that. Not 1 plus cosine x, just cosine x times x squared. Let's see if we buy it. I don't know if I buy it. It is without the plus 1. Yes, okay. Oh. So the thing I was worried about. No. Yeah. So normally you're stuck with this. Normally. However, our interval is from 0 to 1. If you graph cosine, cosine looks like this. Pi over 2 is bigger than 1. So between 0 and 1, cosine is for sure positive. So we can say that on the interval from 0 to 1, cosine of x is less than or equal to 1 and strictly greater than 0. Definitely. Great. I think this will work now. I hope. We'll see. So then if we multiply both sides of this by x squared, 0 is less than cosine of x times x squared is less than or equal to x squared. And then we can invert both sides. And yes, we get the inverse of 0, which is infinity, is bigger than cosine of x times x squared, inverted, is bigger than or equal to 1 over x squared. Yeah, that works. And so then that's a little tricky though. So then we can say that the integral from 0 to 1 of 1 over cosine of x times x squared dx must diverge because this integral from 0 to 1 of 1 over x squared diverges and our function 1 over cosine x times x squared is in fact bigger than or equal to 1 over x squared on the interval from 0 to 1. But we are kind of required to say that last part. Otherwise, it doesn't fly. Interesting. That's a tricky problem. I feel like that is harder than, no, it's probably not harder than you meant it to be, but harder than I might have expected it to be. Yeah, absolutely not. But, well, because I would say if it's comparison and the only thing you have to compare it against is something that's divergent, you're done.
I use that rule, like, he's greater than 1 and version, he's like less.
But that rule is only true if it's 1 over x to the p from 1 to infinity. So I want to be super extra clear about this.
Wait,
Yeah.
problem might have been.
Well, so this integral converges. Yeah, sorry. Maybe you have different problems. Does he give multiple versions of the test? I don't know. Well, so that converges, and then the other. So if you had this one, and then you had this integral instead, I'll leave it to you. But if you have this 1 plus cosine x times x squared, yeah, this would also converge by comparison, because you can show that 1 over 1 plus cosine x times x squared is less than 1 over x squared, because 1 plus cosine x is always bigger than or equal to 1. So maybe you all had different problems, but this would definitely, right? This inequality you can get from saying 1 plus cosine x between negative 1 plus 1 and 1 plus 1, and then multiply everything by x squared. 0 less than or equal to x squared times 1 plus cosine x less than or equal to. Where's my brain working now? Now am I losing it? No, I'm not losing it. Maybe I am. Maybe I'm just losing it. Sorry. I feel like this should be obvious to me, but oh, I see the problem, man. That is a problem. Yeah, this is a problem here that I don't want to deal with. So, how about we talk about it after you get your test time? But interesting problem either way. So let's see. Someone wrote, I did this, but at the moment of inverting, I forgot to invert the sign, so I compared it to negative 1 over cosine x squared. I don't. I have no idea if you're going to get marked right or wrong. That's never a question I'm good at answering because I'm not the one grading for exams. So I don't know. You might be marked wrong, you might not, but not a question I can really offer any insight to, unfortunately. Fun problem. I mean, I kind of like this problem actually. It's very kind of makes you think. Yeah. Oh yes, definitely. So back to polar coordinates and how exciting they are. So one of the things we often do, and actually this is something that we do a lot of when we're trying to change the type of coordinates we're using to integrate a double or triple integral. Sometimes it makes a lot of sense to use rectangular coordinates. Sometimes it makes a lot of sense to use polar coordinates with the third coordinate making them cylindrical coordinates. Or sometimes it makes sense to use something called spherical coordinates, which you will learn about in the future. And being able to convert between them is really necessary to change from one coordinate system to another coordinate system. So let's convert. Convert each Cartesian equation to polar. So this is where it's going to be really important to remember that those relationships. X is equal to r cosine theta, y is equal to r sine theta, and x squared plus y squared is equal to r squared. And sure, I suppose I would really write it this way. Tangent of theta is y over x. I don't think it's any more useful to remember it the other way. So let's look at this equation. X equal to 3. How exciting. We know what it looks like. It's a vertical line. A vertical line makes a lot more sense to describe using rectangular coordinates, but if you wanted to, you could also describe it using polar coordinates. So if we write this as, well, I'm just going to replace x with what it's equal to in terms of polar coordinates. I'm going to have r times cosine theta equal to 3. And then solving for r, because usually, kind of like how we often write y as a function of x, we usually write r as a function of theta. Almost always. So we're going to write this as r equal to 3 divided by cosine theta, or r equal to 3 secant theta. It's kind of neat. And you really can't think about it this way. So if I go over here, 1, 2, 3, right, here's my line x equal to 3. But we can also think about plotting some of these polar coordinates. So right here, here's the point where I really feel like almost theta should be written first because I'm almost always thinking about plugging in theta and then getting out r, but it's not the way it's written, unfortunately. This point here where theta is 0, secant of 0 is 1, and 3 times 1 is 3. So we get our r comma theta exactly right there. And then if your angle was something like, I don't know, sure, pi over 3, that point right there is going to be r comma theta, which is going to be 3 secant of pi over 3, comma pi over 3. Secant of pi over 3 is 2. That's 6 comma pi over 3. So in the pi over 3 direction, we went a length of 6. And the steeper your angle gets, the longer your secant value gets. And as the angle approaches pi over 2, the value of secant gets infinitely large. So if your angle is like 89 degrees, your secant value is going to be super big to get way up there. It's kind of neat. It's kind of weird. Let's look at some other ones. They start off boring, they get less boring really fast. What about y equals x? So I think there's an easy way to answer this problem and a less easy way. For any line through the origin, it's just some angle. And we know for the line y equals x, what's the angle? You could say it. What degrees? What radians? Everyone's so quiet. I know you all know what this angle is. I know you just don't want to say it. What angle is that? A good old thank you for someone in the chat being yes. It's easier to write in the chat though than say words out loud. Pi over 4. And that's always the angle, and then r can be anything. So just like here for the line x equals 3, y can be anything. So we don't end up having the variable y, or y is what's called a free variable. Here, this equation is theta equal to pi over 4. And technically, you could really write theta equal to any 5 pi over 4 or 9 pi over 4 or any, you could keep adding pi to it, and those would all be correct. But this is the right way to write it. You could also find it by doing the work. You could have said y is r sine theta, x is r cosine theta. Divide both sides by r cosine theta to get the r's canceling, and sine theta over cosine theta, which is tangent theta, equal to 1. And the solution to that is theta equal to pi over 4. But I think if you can see the angle, you're good to go. Now, if your line is less nice, your angle is less pretty. For example, if your line was something like y equal to 4x, well, then things are not great because now your r sine theta is equal to 4 times your r cosine theta. And dividing both sides by r cosine theta gives you tangent theta equal to 4. And so then your angle is the arctangent of 4, which I don't know what that is. I can draw it though, because I can draw y equals 4x over 1 up 4. Maybe I can draw it. We'll see. So there's your angle, theta equal to the arctangent of 4. That's the equation of that line in polar coordinates. Someone wrote something in the chat here. So y equals x is a line, but we're making it a polar coordinate. We're not finding just a point. When we write the equation theta equals pi over 4, it's kind of like writing the line x equals 3. We still get a line there because for this x equals 3 line, y can be anything. For this theta equals pi over 4 line, r can be anything. So we get the points like 1 comma pi over 4 and 2 comma pi over 4 and any value comma pi over 4. Just like on this line, we get points like 3 comma 1, 3 comma 2, 3 comma negative 3, etc., etc., etc. The missing thing, if it's not in your equation, gets to run over all possible values it's allowed to take on, which is usually everything from negative infinity to infinity. And I should point out over here, you get points like negative 1 comma pi over 4, and so on and so forth. So yeah, we get the entire line, not just a point. Now, things are weirder when your line doesn't go through the origin. In fact, I feel like almost not worth discussing, but let's look at one example. So let's say we have the line y equals 2x plus 1. Well, fortunately, the process is always the same. You take your Cartesian equation and you replace every y with r cosine, sorry, r sine theta, and every x with r cosine theta, and then you try to isolate r, like we try to isolate y when you're writing y as a function of x. So here we would just say r sine theta equals 2r cosine theta plus 1. We bring the r things to one side, so we'd have r sine theta minus 2r cosine theta equal to 1. Factor out the r, and then divide by what's left over. So here, the equation of this line is r equal to 1 over sine theta minus 2 cosine theta. Now, fun fact, relatively new fact, Desmos will graph polar things as well. Didn't always used to be true, but it is. And I think if you do it this way, so let's try. So we have r equal to 1 divided by, oh, look, there's r equals 1, just a circle. Seems reasonable. But if we do 1 divided by, whoosh, okay, sine of theta plus, or sorry, minus 2 cosine of theta. Yeah, that looks like the right line. Let's check. If we graph y equals 2x plus 1, yeah, they're the same. How nice. Kind of cool. Anyway, let's look at a few more. So let's look at a few more actual realistic things here. So, paper. Here's one that should be obvious, probably. So my equation is, I was lettering these things somehow. This is E. My equation is x squared plus y squared equals 25. And again, I feel like this is one you can just kind of know. So this equation is what kind of equation or what kind of graph? A circle. And it's a circle with what radius? 5. So our polar equation is probably going to be r equals 5. And it is, because if we start replacing things here, well, x is r cosine theta. Well, in fact, I'm doing this the dumbest way possible. Let me show you what I mean. And maybe not the dumbest way possible, but I'm doing more work than I need to do. Because I should have remembered that I could have just said x squared plus y squared is r squared. I don't have to do this work of saying this is r squared cosine squared theta plus r squared sine squared theta equal to 25. And then that's r squared times 1 equal to 25. I should have just straight from the jump said, oh, that's r squared. So if you're converting from rectangular to polar or polar to rectangular, if you see an x squared plus y squared, immediately say that's r squared. Or if you see an r squared, immediately x squared plus y squared. So then I'm going to get r equal to just 5. We don't say plus or minus 5. We just say 5. Although technically, you could say that it would also be right to write r equals negative 5. That would also give you the circle of radius 5. It's just kind of the not typical way of doing it. Okay, what time is it? Oh, we got so much time. Oh, you get to see so many fun graphs. So, not that I'm graphing any of this, because I know you know what a circle looks like. But this next circle is going to be a little more interesting. Let's see. Let's be smart about this. I don't want to do that one. Let's try this one. X squared plus y minus 3 squared equals, let me be smart here. Yeah, 9. Also a circle centered at 0, 3 with a radius of 3. There is something interesting about this though. So let's take a look. So I'm going to change this to polar coordinates. Um, yeah, I would probably multiply it out before changing it to polar coordinates, to be honest. I'm going to make my life easier. Y minus 3 squared is going to be y squared minus 6y plus 9. Why is it better to do this first? Well, look at this. Doing it this way first, I see x squared plus y squared, and that gets to become r squared right away. On the other hand, if I plugged in r cosine for x here and r sine for y there, and then squared it all out, it'd just be more to deal with. So it's perfectly fine if you see a way of getting to x squared plus y squared before changing things to polar, totally fine to do that. So this is going to be r squared minus 6 times y, which is r sine theta, and the 9's cancel to give me 0. Okay, how do we solve for r here? Well, what we typically do is we actually factor. So we're going to say we have r times r minus 6 sine theta. So either r equals 0, which isn't particularly interesting, that's just the origin. So I should point out, r equal to anything except for 0 gives you a circle of some radius. But r equal to 0 gives you just a single point, the origin. Or we get r equal to 6 sine theta. And interestingly, r equal to 6 sine theta gives you this circle centered on the y-axis. Let's explore this a little bit more because this is where things start to get a little bit more interesting. So if I was told to graph r equal to 6 sine theta, and I didn't already know it was a circle, here's what we would do. And this is where things start to get a bit tricky. So we're going to plot some points here. We're going to plot some polar points. So I'm going to pick the usual angles. I'm going to pick theta equals to 0, pi over 6, pi over 4, pi over 3, pi over 2. Yeah, we might as well go 2 pi over 3, 3 pi over 4, 5 pi over 6, and lastly, pi. Well, we'll talk about that. And then we're going to find sine of that times 6. So sine of 0 is 0, so we get 0. Sine of pi over 6 is 1/2. 6 times 1/2 is 3. Sine of pi over 4 is root 2 over 2. So we get 3 root 2, which is about 4.2. Sine of pi over 3 is root 3 over 2. So we get 3 times root 3, which is about 5.2. Right? Yeah, 5.2. And then we're good to go. Sine of pi over 2 is 1, so 6 times 1 is 6. And then the rest of these are just the same values in the reverse order. Sine of 2 pi over 3 is also root 3 over 2, so we get 6 root 3 over 2, which is approximately 5.2. Sine of 3 pi over 4 is also root 2 over 2, so we get 3 root 2, which is approximately 4.2, maybe 4.3. And then finally, we get 6 times 1/2 here, which is 3, and then 0. Okay. So now I need to find that damn ruler of mine. I should have brought my polar graphing paper, but I didn't. Okay, so I'm going to draw kind of radiating lines outward in the directions of each of the angles I picked. So here's pi over 4. And again, I'm eyeballing this. Here's pi over 6, which is like 30 degrees. And here's pi over 3, which is like 60 degrees. A little bit steep there, James. And then on the other side, same deal. Let's do that one first. Actually, I'm not going to do those yet. We'll fill those in a second. So in the theta equals 0 direction, we just get 0. In the theta equals pi over 6 direction, we get 3. But be careful here. I'm not going to go over 3 and then up, because that would be longer than 3. I have to go over 3 and then think about going radially to right there. That's a length of 3, approximately. And then for theta equals pi over 4, I'm going to go over to 4.2 and then go up radially to that point there. I probably overshot it there a bit. This is why we don't graph these this way, by the way, because it's terrible. And then for pi over 3, we get about 5.2. I could probably go up here instead. I could be smart. It's going to come down about like that. And then finally, at pi over 2, we get 6. So then I'm going to connect these all together and check it out. I get half of a circle. And then I'm not going to torture myself by doing the other half. You can see that if my angle is 2 pi over 3, I'm going to get the same distance. So I'm going to get kind of like this point over here, and then that point over there, and then that point over there, and it's going to come back down this way. Here's what I think is really interesting about this. My angle theta, to get the whole entire circle, theta went from 0 to pi, not 2 pi. And that's just oh, I forgot to plug in my computer. I should do that before it stops working. So I always thought that was interesting when I first learned this, that, oh yeah, you get the whole circle by only going from 0 to pi, not 0 to 2 pi. And that is just a thing that is true. So what I'll say more generally is that when you have r equal to a multiple of sine or a multiple of cosine, it's always going to be a circle. So I'll just tell you, actually, I'll show you here in a second. If I was graphing something like r equal to 4 cosine theta, here's how I actually graph this. I'm going to plug in two values, theta equals 0 and theta equal to pi over 2. One of those is going to give me the origin, and one of those is going to give me the other point opposite of it on this diameter. So if I plug in 0 for theta equal to 0, my r is going to be 4 cosine of 0, which is 1, which is 4 times 1. And then for theta equal to pi over 2, not that I really need to do it, but r is going to be 4 times cosine of pi over 2, which is 0. So this tells me that my circle has a diameter of 4. And the endpoints of that diameter are the Cartesian coordinates 0, 0, and 4, 0. And then we can just draw the circle. Now, something that's interesting about the cosine one specifically is when we start off, we're starting off in this direction. This is theta equal to 0, r equal to 4. And then as we increase our angle, look what happens. Here's theta equal to pi over, I should be writing this more smartly. Theta equal to pi over 3, and my radius is, sorry, pi over 6, apologies. And my r is 2 root 3. And then theta increases, I get another point. Theta increases, I get another point. Theta is pi over 2, I'm there. And now check this part out. When I do theta equal to, say, 2 pi over 3, I'm pointing up this way, but my value is negative. So when theta is 2 pi over 3, r is 4 cosine of 2 pi over 3, which is 4 times negative 1/2, which is negative 2. So I'm going that way, but I'm actually going in the opposite direction, and I'm ending up right down there. So that's how you get the other half of this cosine circle. But really, you don't have to do all that, right? And actually, let me show you here, because I think it's actually, I just think it's super duper neat. So if you graph some positive multiple of cosine of 1 theta or cosine of theta, you get, I've made this more complicated than I need to, because I was having a lot of fun with this earlier, because if you turn these all on, I'm sorry, I have to, was neat. Like, look at that. Isn't that fun? So we'll talk about this in a second, but what's happening here is all these graphs are cosine of n times theta or sine of n times theta. and one of them has a negative, one has a positive coefficient. So if we go back down to n equals 1, which is less exciting, and we have a equal to 1 as well, so this is the graph of just r equal to cosine of theta. This is the graph of r equal to sine theta. So, right, centered on the y-axis. Here's the graph of r equal to negative cosine theta. Same circle, but now it's centered on the left side of the x-axis instead of the right side of the x-axis. And similarly, r equal to negative sine theta is centered on the bottom of the y-axis instead of on the top of the y-axis. That's always how these circles end up working, which is kind of neat. Yeah, how much more do I have to say here? Sorry, I just want to make sure I'm saying all the things before I get too excited about the thing I'm excited about. Where'd you go? Sure. Yeah. Okay. All right. So that's an interesting polar graph. So in my opinion, there's probably 3 types of polar graphs you actually need to be aware of to be able to graph them. And one type of them are the ones we just talked about. So I'll point out that in general, r equal to a times cosine of theta is a circle with, I don't want to say this the right way, with endpoints, diameter endpoints at the origin and a comma 0. And if a is positive, that means we're on the right side. If a is negative, that means we're on the left side. And similarly, bless you, r equal to a sine theta is a circle with diameter endpoints at 0, 0, and 0, comma a. Again, if a is positive, it's above. If a is negative, it's below. And again, more generally for both of these, if you're graphing r equal to a cosine theta or r equal to a sine theta, all you have to do is let theta equal 0 and pi over 2 to find those diameter endpoints. So graphing a circle is not too bad. Actually, graphing a circle like this is not too bad. But then there's some other graphs. Ooh, yeah, let's look at this one. So there's 2 other types of graphs that we focus on: roses and cardioids. Let's talk about the roses first. So roses. Let's start by graphing one that is not too terrible. R equal to, sure, cosine of 2 theta. So actually graphing this the long way is terrible. Here's what I mean. I'm going to plug in a few values of theta. Specifically, I'm going to plug in theta equal to 0. If theta equals 0, let's just make a table, James. Let's be smart about this. R is going to be 1. And then if theta equals pi over 4, my R is going to be cosine of pi over 2, which is 0. It doesn't really help me because I don't how am I getting from there to there? I want to pick one intermediate point. So I plug in theta equal to pi over 8. I'm going to get cosine of 2 pi over 8, which is pi over 4, which is root 2 over 2. So when my angle is half of 45 degrees, so not 45 degrees, but half of 45 degrees, my value is root 2 divided by 2, which is about 0.7. So what's happening is I'm getting something that looks like this. Although I've probably drawn it too exaggerated. And then this keeps happening for theta equal to 3 pi over 8. I'm going to have cosine of 3 pi over 4, which is negative root 2 over 2. So if I'm pointing in now this direction, 3 pi over 8, which is like that, then I'm going negative, so I'm going down this way, like over here. And then if I plug in theta equal to pi over 4, I get cosine of 2 pi over 4, which is cosine, whew, sorry, not pi over 4, pi over 2, apologies. Cosine of pi, which is negative 1. So in the pi over 2 direction, which is up, I'm going negative 1, which is down. So I'm getting like that. So what happens is this keeps happening. I go this way, 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 I go this way. Which is kind of horrible. Here's what you really ought to know about roses. R equal to either cosine of n times theta or sine of n times theta. And you can have a coefficient out in front, which will just make it larger or smaller. So if n is even, like in this previous example, in this previous example, n was 2. If n is even, you get twice as many petals as the value of n. So n was 2 and we got 4 petals on our rose. If n was 4, we would have gotten 8, and so on and so on. And I'll show you in a moment. So we get 2n petals. The way I always think about this is if it's cosine, for cosine, the petals are on axis. For sine, the petals are off axis. I will show you in a moment. I would draw this for you, except my drawings for these always suck beyond compare. Like it's just they're hard for me to draw. Also, and probably importantly, we get 2n petals and they're evenly spaced. So when I'm looking at this picture here, I'm thinking of this petal, these 4 petals, they have their kind of endpoint on axis, and they're all, well, since there's 4 of them, they're all 360 divided by 4, which is 90 degrees apart from each other. And lastly, to get the whole graph, we have to have theta go from 0 to 2 pi. So let me show you. Let me show you with my fun Desmos stuff instead of with drawings, because I can't draw this. So let's look at a cosine of n theta. And let's make a little bit bigger, just, that's fine. So if n equals 1, sorry, if n equals 2, we get the graph I just talked about. Which, okay, I did an okay job of drawing it, right? Could have been better, but fine. If n equals 4, 8 petals. And the cosine ones have to live on axis, meaning the 4 original ones are going to be on the y-axis and x-axis, and the other ones are going to be evenly spaced. So all of these petals are 45 degrees away from each other. And then if n equals 6, same deal. On axis, they're all 30 degrees apart from each other, or whatever the pi over 6. And you keep going, right? N equals 8, you get 16 of them, still on axis. Now, if we change the sign, same number of petals, same spacing, off axis. Oops, turn off. So they're all off axis. You don't have the petal lined up symmetric on the axis. And if you go down back to say 2, it looks like that. So basically it looks like you have, so for this one, the spacing of each petal is 90 degrees apart. For cosine, they're on axis. And for sine, you've rotated it by half of 90 degrees, 45 degrees. Same deal over here. these are all 45 degrees apart, and you shifted this one by half of 45 degrees. I hate drawing these, as you might have gathered, because I haven't drawn any of them. I've said I hate drawing them, but they are hard to draw. They're hard to draw. They're hard to draw without like because they shouldn't overlap each other at all. And when I start drawing them, my petals just get to be too fat, and they want to like be on top of each other. That said, they're not hard to visualize, right? We can see this pretty easily. Um, it is interesting to me here. The theta has to go from 0 to 2 pi. In fact, let me actually do a little bit more of this. So let's go back to, let's say here. So we're going to start at 0 and we're going to go just to pi over, ooh, that's interesting. So there's 0 to pi over 4. I got one of those 8 lobes, which makes sense, right? Because pi over 4 is 1/8 of 2 pi. If I add another pi over 4, I get 2 of the lobes. Look at the order they're getting drawn out in. If I go to 3 pi over 4. In fact, let's go to, sorry, 5 pi over 8. So look at that. It's done. I can't really point at the screen. It's done, right? This loop first, and then that loop there, and then it's making its way up to do the first half of that second loop. And it just keeps going. So, sorry, here. We're going to go now to say, let's go a little bit more. Let's say we go to, oh my goodness, can I do this? Maybe not. Sorry. Nope, I'm done. I've clearly blown it here. There we go. Pi over 2. Oh, we did that already. Pi, just sort of pi. There's half of it, but it's like the weirdest half you could imagine, right? You might have imagined it being somewhat like more symmetric. And then you can go to 3 pi over 2. And then finally all the way to 2 pi. Oops, let's just delete that. So anyway, it gets drawn out kind of in a not maybe seemingly obvious order if you haven't practiced doing it. But I do think you could play with this, right? You could all use Desmos in this way and kind of see like, oh yeah, it gets drawn out this way. And in fact, if you're smarter about this than I am being, let me try and do something cool here. I'm going to change the theta to a T. You didn't let me, why don't you want me to add? Oh, because you're being a jerk. Let's use a different letter than T. Usually when you use a different letter, it'll offer up to you to do some sort of uh, slider thing, which I can't think of what it's called now. Nope, you're really just being that. Fine, I'll use N. And then if we let N go, no, that's not going to work either. Sorry. Sorry. You could probably figure out a way to make it so your angle just draws out, which is kind of interesting. What if I try doing it down here instead? Sorry, I really think this is worthwhile. So if we did R equal to sine of T, nope, you really don't like that, do you? K, nope, fine. I'll play with it later and figure it out. Anyway, so but then what I wanted to say is for the sine one here, which I just deleted. Yeah, well. Oh, so then the odd ones. We didn't talk about the odd ones yet. That's where I was going to go next. So the odd story is a little bit different. If n is odd, we get n petals evenly spaced. Every one of these has one petal that's on an axis. So both sine and cosine have one, exactly one on axis petal. And interestingly here, theta goes from 0 to pi. That will give you the entire graph. So let's spend a moment looking at that, and then we will probably call it a day. We'll talk about cardioids next week. And then the other length stuff or whatever. So, sorry, let me get back to my graph here. So I just want to show you guys this and then we can call it a day. So we look at r equal to cosine of, say, let's say we're looking at 3 theta. Gosh, why are you being so difficult? There we go. So there's r equal to cosine of 3 theta. So they're evenly spaced. They're all 120 degrees apart. And you have one on axis 1. And I deleted it, but let me rekindle it here. For r equal to a times sine of n theta, it's also 3 petals evenly spaced, and one of them is on an axis. So how would I draw that? How would I know which axis to draw it on? Well, that's where you just do a little bit of work. So if I was trying to draw, and I'll torture myself here. If I was trying to draw r equal to cosine of 5 theta, cosine is usually pretty easy because if you plug in theta equal to 0, you're going to get r equal to cosine of 0, which is 1. So I know if I start drawing this, my one on-axis petal is going to be on the positive x-axis. And then my other 5 petals are evenly spaced 72 degrees apart, which is not fun to draw. I don't want to draw. Other 5 petals. Like that. Except, actually. We can look at the picture. Cosine. There's cosine of 5 theta. Sine is usually more interesting though. So, sorry, if I was going to do r equal to sine of 5 theta, well, plugging in 0 isn't helpful because sine of 0 is just 0, and that doesn't tell you really a direction you're pointing. On the other hand, if we plug in theta equal to pi over 2, which is in the up direction, well, sine of 5 pi over 2 is positive 1. So in this example, the sine one has its on-axis petal on the positive y-axis. But contrastingly, if it's r equal to sine of 3 theta, we again pick theta equal to pi over 2, and sine of 3 pi over 2 is negative 1. So this one starts on the lower y-axis, and then your other petals are, there and there. So sine's always kind of a crapshoot. Or really, sine changes which part of the axis is on every other one. So like if you look back at your graph here, for cosine, doesn't matter. Cosine of 5 theta, positive x-axis. Cosine of 7 theta, positive x-axis. Cosine of 9 theta, positive x-axis is what we're up 9, James, not 10. The on-axis petal is on the positive x-axis. But for sine, it alternates. Sine of 9 theta is on the positive y-axis. Sine of 7 theta, negative. 5 theta, positive. 3 theta, negative. So these roses are not too terrible to draw if you're moderately good at drawing things. If you're not that good at drawing things, they're kind of terrible to draw. But they're not that terrible to visualize, right? We can see what these things look like. They're just all these little loopy things pointing out from the origin, and the number you get is either the coefficient of theta if it's odd, or twice that coefficient if it's even. And they're not that much more complicated. Next week, we'll talk about the other kind of graph, which is a little weird, and then we'll talk about finding lengths of these things and maybe area encompassed by them or enclosed by them. The area part's kind of weird. That's next week. I'll see you all then. And if anyone figures out exactly what that cosine improper integral thing was, feel free to send it to me and I'm happy to look at it.